Hello. Yeah, hi everyone. Good evening. Just confirm once if my audio is clear, screen is clear. Wait, let me present the screen. Just confirm once that my screen is visible so that we can start. Wait a minute. Okay. So good evening, guys. So today we are going to take a demo class for recursion. It's the demo class for level 2 in TLE Eliminators. TLE Eliminators has been running the course of competitive programming for around now 3 years, and we have already completed around 10 batches, and we are going to start with our 11th batch. So to get all of you accustomed to what we actually, how we actually teach in TLE Eliminators, this is the video regarding the level 2 course, and we are going to learn about recursion today. A basics of recursion, but yeah, very helpful. Just confirm in the comments once that is if my audio is clear and the screen is visible to each and every one of you. Yeah. So let's get started with the recursion. So first of all, before starting with the recursions, we will just go with a quick recap on what actually functions are. So a function is a block of code which runs the code inside with the parameters it is given. So like for example, you can look up to this structure. It is a function whose return type is int. It is taking two parameters, integer a and integer b, and it is returning a plus b. So this actually what a recursion is. Now talking of recursion, what actually a recursive function is. So recursion happens when a function calls itself on a different set of input parameters, and it is used when the solution for current problem involves first solving a smaller subproblem. What actually I mean by this? Let's suppose I give you all a problem to solve, okay, and this is a problem, and you are a bit confused that okay, I can't find what to do with this problem. I can't think of any greedy approach. I can't think of anything else. I can't think of any algorithm as such. Then how to solve this problem? Then if you can divide these subproblem into smaller subproblems, divide this problem into subproblems, so basically dividing this into smaller subproblems, and if you are able to solve the smaller subproblems and combine the result of this to form the result of the original problem, then it's called that you are using recursion. We will take examples, but this is what actually recursion does. That you have a bigger problem, you are dividing it into subproblems, and then from the result of subproblems, you are getting the result for your original problem. This is what recursion is. So recursion is basically when a function calls itself on a different set of input parameters. And yes, like for example, this is a very basic code of recursion. We have a function to find a sum of numbers from 0 to the given parameter. We have been given a number n, and we want to find the sum of all the numbers from 0 to n. That is 0 plus 1 plus 2 plus 3 up till n. This is the requirement. Now, all of us can write the direct code of it, isn't it? We can simply write like for loop from I equals to 0 to n, and we can initialize our answer to 0, and every time in our inside our for loop we can just increment our answer with I. This is something that we can always do, isn't it? Now, I want you all to write the same thing via recursion. The same code via recursion. So let's see how we can do this. Let's understand how we can do this. So, what is a larger subproblem in front of us? We have a subproblem. We want to find the sum of all the numbers from 0 to n, right? Now just tell me one thing. If I just give you that, okay, hey, from number 0 to n minus 1, the sum of numbers is, let's suppose, answer 1. If I, let's suppose, give you, just forget about what we are actually doing. Just imagine that we have a problem where we need to get the sum of numbers from 0 to n. And I tell you that, okay, I have the sum of numbers from 0 to n minus 1. I already have this and the result is answer 1. Now just tell me, will you all not be able to find the sum of numbers from 0 to n with the help of this result? Is this possible? Isn't it possible that we can find the sum of numbers from 0 to n with the information of sum of numbers from 0 to n minus 1? Is it possible? It is, right? So, how? We know that from 0 to n minus 1, my answer is answer 1. So to get the sum of numbers from 0 to n, it is simply answer 1 plus the nth number, that is answer 1 plus n. Once we write this, we know that we have the sum of numbers from 0 to n, because what actually is 0, 1, 2, 3, 4 up till n minus 2, n minus 1, n. We were required to find the sum of all these numbers, right? Now I am telling you that I already have the sum of all these numbers. This is actually given. It's answer 1. So to get the required result is nothing but answer 1 plus n. Isn't it? So recursion is something that will give you this result, answer 1. Once you have this, you can just combine it with n and return the result. We will see how we can write these, but this is what actually recursion is. So you were having a bigger subproblem, that is you wanted the sum of n numbers. Now what recursion did? It gave you the sum of n minus 1 numbers, and you only required to get the combine it with the last number n and return the result. So this is what recursion is. So before understanding this code, before understanding what actually is written here, we will understand the basic structure of a recursive function. What actually we need to write a recursive function, what actually we need to have to write a recursive function. These are some of the basic structure. This is the basic structure. So first of all, the parameters to start a function. So whenever we are talking of function, we will require parameters, right? The second, we will require appropriate base cases to end the recursion. I will come to this point later. Let me just go through the other points and I will come to this later. The next is recursively solve these subproblems. Okay. So as we discussed that we were having a larger subproblem. We were having a larger problem. We will divide it into subproblems. We will again divide the subproblem into subproblems. We will again divide it till the end. So, and just combine the results. So that is, we are solving the subproblems recursively. You will get it more clear once we proceed further. Then at the end, process the result and return the value if any. Okay, so these are the 4 basic structure of a recursive function. Now let's try to understand the structure via the examples that we already had. We have this example, right? We have a function, integer function, that is taking an integer parameter as the input. Then we have something like this. This is something written. Let's just copy it down. We will see what it's written. If n less than equals to 0, then return 0. Okay, let's not get into this as of now. Then wait a minute. Yeah, then we have a return statement that is calling this function again, but to n minus 1, that is to a different set of input parameters, and we are returning the result of this function plus n. So we have something like this: return f of n minus 1 plus n. So this is what a recursive function is written. Let's now go through it and what are the components that it contains. So first of all, we have a function that is containing the parameters. Then this is something that we call as base case. We will get into it more. Let's leave it till here. Over here, we are recursively calling the subproblem. So recursive call of a subproblem. And via this, we are just combining the result. I also say it as small calculation part. So let's see what this function actually does. Let's try to imagine what this function is actually doing. So what we have a function. Let's suppose for now the value of n is 3. So for now we have a function f of 3. We called a function with input parameter 3. So now what this function did, is the value 3 less than equals to 0? The answer is no. So now it will call to f of n minus 1. So it calls to f of n minus 1, that is a call is given to f of 2, and that is to input parameter 2. From here again, since 2 is not less than equals to 0, there will be a call to f of 1, and similarly a call to f of 0. Now once a call to f of 0 is made, just check the function. The first line of function contains a check that is the value of n less than equals to 0. If it is, then simply return 0. So is the value of the input parameter n less than equals to 0? The answer is yes. So what it will do, it will simply return 0 over here. Now once it is returning 0, so what actually function is returning, what actually this function is returning. This function is returning the result of the function call to a smaller subproblem plus the value of input parameter at that point of time. So if we made a call to f of 0, we got our result as 0. Now what will this f of 1 return to this? F of 1 will return the result of the lower subproblem, that is 0, plus input parameter at that point of time, which is 1. So it will simply return 0 plus 1, which is equals to 1. Is it clear? Now what f of 2 will return? So f of 2 will return the result of the smaller subproblem that smaller recursive call that it made, that is 1, plus the input parameter at that point of time, which is 2. So it will simply return 3. And what will f of 3 return? F of 3 will return 3, that is the result from the recursive call, plus n, which is 3. So plus 3, which is equals to 6. So finally the final result call will be 6, and this will be our answer, because this was the first function that we called, isn't it? We as a user called this function, so this function will return the answer to us. Just try to imagine these calls are made by the function itself, function within itself. These are the calls, these are not the calls that we as a user made it. We as a user made a call to function with input parameter 3. Now the function decided that, okay, this problem is looking a bit large. I can't find the sum of numbers till 3. Let me get the sum of numbers till 2, and I will add 3 to it and return the result. Now this f of 2 argued that, okay, 3 was looking bigger to you. I know that my input parameter is lesser than 3, but still it is big. It is 2. I can't get numbers, the sum of numbers till 2. So what it made a call to 1. And similarly 1 made a call to 0, and 0 told that, okay, for me the number is not too big, I need to simply return 0. So it simply returns 0 from here. And once 0 is returned, now one f of 1 knows that I can return the result because I only need to add 1 and that is a simple task for me. So it simply adds 1 and returns the result. Similarly for 2, it knows now, since it knows the result till number 1, so it can simply add 2 and return the result, and similarly for 3. So this is how the function is helping itself to solve a problem, and this is what recursion is. These calls that a function is making to itself is called a recursive call. And this process is something called as recursion. So this is what actually recursion is. Now, how to solve the questions of recursion? So first, let's understand this tree view of this recursion, and once we are done with that, we will see how we can actually solve the question of recursion. So once you start solving the questions of recursion, the first thing, and as a beginner, that you should do is when you are solving some beginner level questions, always try to draw a recursive tree. Recursive tree is something that will help you to imagine that how actually the function is running. This is something that is called as recursive tree. This is actually a recursive tree. That is a function call of with input parameter 3 was made by the user. It made a call to 2, then it again made a call to 1 and 0 and so on. This is what actually recursive tree is. So recursive trees are useful to help us understand how the function acts. So once you are starting with the recursion, it's always recommended that you start drawing the recursive tree of your own, so that the things become clear to you. You are able to imagine the things. One, you can just look up to this word mind map. Once your mind becomes active to map the things automatically, you don't need to draw the recursive tree. But to the ones who are starting, it's very important and it's very much recommended to draw a recursive tree for at least 3 to 4 questions, not with bigger input parameters, to with the smaller input parameters. Like for example, I will not tell you to draw a recursive tree for this particular function with input parameter 100. That is something not recommended. You don't want to fill up the pages, isn't it? So try to take the input parameters as small as possible. Now don't take it as 0, okay? Don't take it as 0. Try to take it a parameter such that you can draw up to 4 to 5 levels, and the things become clear to you that what actually is taking place in the function, how actually the call is making, how actually the something is returned, and something like that. So that the mind is able to map that how actually the things are running, because it's very much important for you all to understand how the recursion is actually taking place. Okay, so now just let me talk on this part now, this base case part, and it's like a super important part. Let me tell you why. Now just imagine that we made a recursive call to f of 3. We made a recursive call to a function, we made a call to function f with input parameter 3. It made a recursive call to f with input parameter 2, and then it made a recursive call with input parameter 1, and then a call was made to 0. Now just imagine if 0 would have not told that this problem is doable for me, and if it would have called to something like f of -1, so that would have gone a blunder, right? It cannot make a call to f of -1. We wanted the sum of numbers from 0 to n. From where did this -1 came? So this was not something that is required, isn't it? So every time when you are calling a function, you need to decide at which part the call needs to be terminated. Let me repeat. You need to remind yourself again and again that what is the smallest sub problem that you can solve of your own. You don't want to make a recursive call for that. What is the smallest sub problem that you can solve from your own? You need to identify that, and once you are able to do that, just make a return statement from here, and this is what we call as base case. This is super important for recursion. Like for example, over here I knew that if n is less than equals to 0, that is if n is becoming 0, so I know that I can return 0 from here. I don't want to make any recursion calls from this particular step, So I simply returned 0. That is, for n equals to 0, my function will not run more. It will simply return 0 from here, and it will return the things to the recursion call. Like over here, it made a return 0 to this f of 1. So I need to decide these base cases, and you all can understand the gravity of this by just looking that if f of 0 would not have returned 0, we would have made a call to f of minus 1, and that is something that would not have been feasible, right? So this is something that you need to be very careful, that what is the base case that you are taking, what is a recursive call you are taking, because every time you are making a recursion call, just keep in mind that the parameters should be same, the number of parameters should be same, the type of parameters should be same, and this function is doing the same thing. Like the motive of this function is to do the same thing as this particular function was, that they are the same functions basically. So yeah, that thing is something that you need to be keep in mind. So let's understand one more. Let's write one more recursive code. You all know Fibonacci numbers, right? Fibonacci numbers is something that is known to all of you. So let's write a code that will help us to get the nth Fibonacci number via recursion. How can we get the nth Fibonacci number via recursion? Just try to think how we can do that. So every one of us know that what is the rule of Fibonacci number, that if we are talking of any Fibonacci number, so how do we actually obtain this number? This number is actually the addition of the last two numbers. This plus this is equals to this. Like for example, if we start our Fibonacci numbers with 0, so the first number is 0, the second number is 1. These two is something that is already decided. Now from the third number will be the sum of the last two numbers, that is 0 plus 1, that is 1. The fourth number will be the sum of first and the second and the third numbers, that is 1 plus 1, which is 2. The fifth number will be the sum of third and fourth numbers, that is 1 plus 2, which is equals to 3, and so on. So this is actually we write the Fibonacci numbers. Now, one important tip from my side is, whenever you write the code of recursion, you need to believe on recursion. And once you start believing, just mark my words, once you start believing on recursion, the things will get super easy for you. Now, what I mean by believing, just treat recursion as your friend. Let me show you how. Let's suppose I want the third Fibonacci number. Okay, I want the third Fibonacci number. There is a function f. I am giving it the input parameter 3, and I am expecting the result of the third Fibonacci number from this function f. Okay. Now, I know that for the ith Fibonacci number, if I have the I minus 1th, like if let's suppose this is the ith Fibonacci number. If I want to get this, what actually I want? I want I minus 1th number and I minus 2th number. If I have these two numbers, just tell me, can't I get the result of ith number? I can, isn't it? So, if I want the third Fibonacci number, I will tell that, okay, just make a recursive call to 3 minus 1 and make a recursive call to 3 minus 2 and store them somewhere. Let's suppose int answer 1 is equals to this and int answer 2 is equals to this. So this is basically, we have answer 1 as f of 1 and f of 2 and answer 2 as f of 1. So now if I have these two results, can't I say that my answer or something that I am going to return is answer 1 plus answer 2? Because we know that if we want to get a third Fibonacci number, and if we have the result of second and the first Fibonacci numbers, so in that case we can return, no? Isn't it? We can we can get f of 3 as answer 1 plus answer 2. Now you have to believe that this answer 1 is correct. You have to believe that this function f is giving you the second number, the second Fibonacci number. You have to believe that this f of 1 is giving you the first Fibonacci number, because if you are not believing, you will never be able to write this statement. But if you are believing and everything you have coded is right, you will definitely get the result. Let us see how. Let us just make a recursive tree for this, that we have a function f. Let's suppose we want the fourth Fibonacci number, and this is something like this. We want the fourth Fibonacci number. Okay. So it will make a recursive call to f of 3 and f of 2. Let us first code it down and then we will understand how actually the things are working. Give me a minute. Okay. Okay. Let's suppose we are taking input n and we want the nth Fibonacci number. We have made a function. So we are going to simply print. Let's suppose we have a function that takes this n as input and returns us the nth Fibonacci number. Let's make this function. So we have the return type as int, the name of the function is f, and the input parameter it is taking is an integer n. Now just tell me, just forget about the base case as of now. Let's suppose we made a recursive call to f of n minus 1 and stored its result in answer 1. And we made a recursive call to f of n minus 2 and stored its result in answer 2. So what we will return? We are going to simply return answer 1 plus answer 2. Now what should be the base case? Just imagine. Just imagine what should be the base case. Wait a minute. Yeah. Sorry. Okay. Just imagine what should be the base case. So if you are calling to f of 4, so it will make a recursive call to 3 and 2. This 3 will make a recursive call to 2 and 1. This 2 will make a recursive call to 1 and 0. Now just tell me, don't you know what is the first Fibonacci number and don't you know what is the 0th Fibonacci number? You know, na? If we are, let's suppose, if these are the Fibonacci numbers, so we are telling that this is our 0th Fibonacci number, this is our first Fibonacci number, this is our second Fibonacci number, something like this. We are considering zero-based indexing. So don't you know what is the 0th Fibonacci number and what is the first Fibonacci number? So they are actually the number itself, isn't it? The 0th Fibonacci number is 0 and the first Fibonacci number is 1. And you don't have any sub problem for this. You can't write that f of 1 is equals to f of 0 plus f of minus 1. This is something that you can't write, isn't it? So you have to handle this particular case of f of 1 and f of 0 in the base case itself, and the interesting part is that you already know the answers for them. So can't I write that if n is less than equals to 1, in that case I can simply return n, because if n is 0 our answer will be 0 and if n is 1 our answer will be 1. So if n is less than equals to 1, in that case simply return n. Otherwise make a recursive call to n minus 1, get the answer and store it. Make a recursive call to n minus 2, get the answer and store it, and simply return their addition. So this is, just see, we had n numbers. What is the code we write? What is the code that we already wrote? This is the code we actually wrote, and we will get the nth Fibonacci number. So this is the power of recursion. Let me make a recursive tree for this so that the things get more easy for you. Wait a minute. Okay. So let me make a recursive tree for this. So what we have a function that contains the input parameter for, let's suppose, 3. So this 3, if you just go by the flow. So first of all, a call was made to f of n minus 1, isn't it? First of all, call was made to f of n minus 1, that is f of 2. Now, you are over here, you are not over here. Just ignore this recursive call, this second recursive call. Just ignore this as of now. Okay. Now, from this f of 2, a call was made to f of n minus 1 again. So a call was made to f of 1. And once the value of n, that is the input parameter, is less than equals to 1, so what we are returning? We are returning the number, the input parameter itself. So from here, we will simply return 1. Because since the input parameter was 1, we will simply return 1. But for this f of 2, the answer 1 is equals to 1. But just see, there was one more recursive call for answer 2. So now there will be the other recursive call. So now there will be a call to f of 0, that is f of n minus 2. If you look, there is a recursive call to f of n minus 2. So we have a call to f of n minus 2, that is f of 0. Now again, since the input parameter is less than equals to 1, so we are simply going to return the input parameter itself, that is 0. And since all the recursive calls to these functions are already made, what we are returning from here? We are returning answer 1 plus answer 2, that is the summation of the two recursive calls answers. So this f of 2 will simply return 1 plus 0, that is equals to 1. Okay. Now the other recursive call for 3 was, one was a call to n minus 1. Now second is a call to n minus 2, that is f of 3 minus 2, that is f of 1. There is a call to 1. Now since again the input parameter is less than equals to 1, so we will return the input parameter itself, that is 1. So once we return this results, so can I say that this function f with input parameter 3 will return 1 plus 1, which is equals to 2, and this is our answer. Just look, this was the first Fibonacci number, this was the second, this was the third, and this was the fourth. Like if you just look 0, 1, 2, 3, if you just look by zero based indexing, so this was the 0th Fibonacci number, this was the first, this was the second, and this was the third, and this is something that we are getting. And this is the recursive tree for that. So once you, if you are a beginner, drawing the recursive tree is recommended because the things become clear and deciding the base cases also become easy. But after you gain some experience, these things will automatically come to your mind and you don't need to draw the recursive tree again and again. But it is highly recommended that if you are a beginner, then you should draw recursive tree for at least 3 to 4 questions. And what is the process of drawing the recursive tree? What is the method that you should follow? The method is that you should just look up to the function, to your function, go by the flow of your function, and start with a comparatively lesser input parameter. It's not that you just simply start with, let's suppose I have not started over here with f of 100 or f of 200. I started with something that can be accommodated in this page itself, isn't it? So it's always recommended you can take about, let's suppose, f of 5. F of 5 is something that will give you more clear understanding, but this is but you should not extend it to like f of 10 or f of 20. To even such cases like as well. You should not extend up to this as well. Like f of 5 and f of 6 is something like which is the last that you can take, so that the things become clear to you. Okay. So I hope all of you are now just understand what actually the recursion is, how we actually write base cases, what actually it is doing, how actually we can just understand or mind map what actually recursion doing by drawing the recursion tree, and so on. So let's start with we will discuss one practice problem so that the things become easy for you. So we have the problem with us. The problem is, what are the number of ways we can form target number from the array numbers? Let me explain the question. The question is that you have an array. Let's suppose array is something like this: 1, 4, 7, 2, 3, 9. Okay, and let's suppose it's okay. Let's suppose 6. So these are the numbers you have, and this is actually an array containing the numbers, and you have a target number. Target number is 7. So the question is that in how many ways you can select subsequence from this array such that when you add all the elements of subsequence, the number achieved is equal to the target number. Like for example, if I take 1 and 6 from this array, so 1 plus 6 will give me 7. If I only take 7, so 7 is equal to the target number 7. If I take, let's suppose, 4 and 3, so 4 and 3 will again give me 7. So actually the number of ways in this particular example so that I can achieve the target number is actually 3. So what you need to do is you need to return the total number of ways you can select subsequences such that when you add all the numbers of subsequences, you get the target number as a result. So this actually what question is. I hope everyone understand what question says. So now the question is that how we can solve this, how to think of it. That okay, we have the numbers, we can think of subsequences. We can keep this particular number or not. I don't know. Like if I am keeping this number, I don't know I have 6 afterwards or not, because I can even select 2 to 3 numbers, isn't it? Like I missed one case over here, 1 plus 4 plus 2. It will also give me 7, right? 1 plus 4 plus 2 will also give me 7, right? Yeah. So how to think of it? There can be many cases like, should I keep one or should I not keep one? I am pretty confused, right? I don't know. So what are the options I have? Okay, I am talking of subsequences. I am talking of subsequences, right? So what are the options I have? I can either keep this number or I can exclude this number. These are the only two possibilities, right? It's my choice. It is not like the number will come and beat me if I don't keep it in my subsequence, isn't it? It's my choice completely. I can either keep this number or I can exclude it. So it completely depends on me. So why not make two cases? For in first case, I am keeping this number, and in the second case, I am excluding this number. If I am able to design something in which I can handle both these cases, so the things will become pretty easy, right? Just wait a minute. Yeah. So if I am able to design something in which I can handle both these cases, so the things will become pretty easy. So I need to think of something to design something where I can accommodate both of them. So from here, the choice of recursion comes. This is a very common problem of pick and not pick type. Once you start practicing problems, you will get to listen these words many a times. It's what I would say. It comes with recursion, pick and not pick. So it's a very common type of recursion, and this problem is based on itself, on it. So how we are talking this? Let me draw a recursive tree for this with some smaller example. So let's suppose I have an array where I have these numbers, and my target number is 7. Okay. So what I will do is I will just initialize my index to this particular point. That is, I am starting from current number. So my index value is equals to 0. And till now, as I have not taken any number, so I will keep my sum as 0. So what if we have a function in which the value of index is 0 and the value of sum is 0? Now from here we will make a recursive call. To what? We have two choices, right? For this particular index, either we keep it or we exclude it. So first of all, we will make a recursive call when we are keeping this number. If we are keeping this number, so now we know that we are not going to take this number again, right? Because at max the number can be taken as one time. So we are not going to take this number again. So we will simply shift our index. We will simply shift our index to 1. And since we took that particular number, so our sum will become 0 plus 1, that is 1. But my friend, there is one more recursive call as well. There is a recursive call when we were not taking this number. And if we are not taking this number, we will not take it at any time. So we will simply shift our index, but our sum will remain as it is. Our sum will remain 0 since we have not included this particular number. So you can see that we already have two cases, isn't it? Now again, just look to this function f. We are standing at index 1 and we again have two choices. Either we can take this number or we can exclude it, right? So let's the left hand side recursion call is something that is happening when we are taking the number. So let's take the number. So once we take the number, our index will shift to 2. That is, from 1 it will shift to 2. And since we took the number, so we will simply add this number to our current sum, that is 1. So our sum becomes 7 plus 1, which is 8. And if we are not taking this number 7, so there will be a recursion call to index 2 with the value of sum as 1. The 7 will not get added. Similarly, if you look to this function f1, 0, again over here we will have two recursion calls. The first call will be to index 2 with the number getting added, that is 7 getting added. And the second call will be to index 2 again, but by excluding this number 7. So we will not add anything to this number 0. So the sum will remain as it is. Next, from index 2, again we have two options. We either take it or exclude it. So once we take it, so we will simply make a recursion call to 3. And once we take it, our sum will get incremented by 6. So 8 plus 6 will become 14. And if we are not taking it, so we will make a recursion call to index 3. And since we are not taking it, the sum will remain as it is. Similarly, I am drawing for other functions as well. So f of 3, 7, f of 3, 1, f of 3, 13, f of 3, 7, f of 3, 6. Once we take this number, and the other time we have not taken this. So now just see, once we reach the value of index as 3, we don't have any more numbers to handle. This is index 0, this is index 1, this is index 2. We don't have any index such as 3, isn't it? So once we reach index 3, we know we can't take any more numbers. So that will now become our base case. So this is how we actually decide the base case. We know that since at index 3 we don't have anything to handle, so it will now become as our base case. Now, at our base case, we know that the numbers that we have taken is the max we can take, and we are not going to include or exclude any more numbers. So if at base case our result is not equal to the target number, so we will simply return 0. Why? Because that particular set of combinations have not contributed to our target number. We can't take that particular set of combinations. So we will simply return 0. Else, if the final sum is equal to the target number, so we can return 1, because we know that taking that particular set of combinations can lead us to a subsequence, will actually lead us to a subsequence that will help us to get the target sum, isn't it? So from that we will return 1, because 1 indicates that okay, that is one possible way we can take the numbers, because every path uniquely identifies a set of subsequence. You know that if you have three numbers, how many subsequence you can form? If you have three numbers, how many subsequence you can form? For every number you have two options, so the number of subsequences that you can form are 8. So see, you have 8 base cases to handle. So we know that every subsequence is uniquely handled. So every time we get the end result, end sum as our target sum, we can simply return 1 from it, because that is one possible set that will contribute to the result. So let's do the same thing over here. Since from here we got no result, so we will return 0. From here again we will return 0. So since from these two we got returned 0, so it will return 0 over here. Now from here we will return 1. From here again we will return 0, because the target, the final sum was not equal to the target sum. From here again we will return 0, because the final sum was not equal to target sum. Now again over here, since the final sum is equal to target sum, we will return 1. From here we will return 0, and from here we will again return 0. So just by doing this, over here we have 1, 0, 1. So from here we have 1, from here we have 1. So finally this function will return 1 plus 1, which is equals to 2. And you can see that you have two subsequence that will result to sum 7. Subsequence 1, 6 and subsequence 7. And the end result was also 2. So this is the power of recursion. At every point you had two options. You either included or excluded. You brute forced over all the possible options and got the result. This actually what recursion is. This is the power of recursion. Let me code it down and then the things will get more clear. So let's suppose you have the number and you have the vector, then you take the input of n numbers, and you also take the value of target and simply print the result. So you make one function helper to which you pass the current index that at which you are, that is 0, the current sum that you have, that is again 0, the target sum that you want, and the array numbers. So let's see how we can recode this function. So we have the index, we have the sum, we have the target, and we have the input numbers. Now, what is the base case? Base case is something that we already know, isn't it? If index is equal to v dot size, that is we don't have any more numbers to handle. So in that case, if the sum that we got is equals to target, in that case we will simply return 1, else we will simply return 0, isn't it? So this is something that we that can also be written something like this. Instead of writing these two statements, we can simply return sum equals target. This will do the same thing. If sum is equals to target, it will return 1, else it will return 0. Now we have two options, right? The answer to the first option is stored in answer 1. So what is the first option? The first option is that we are shifting to the next index by taking the value of the current index. So our sum will get incremented by this. The rest two parameters will remain the same. So this is one call in which our sum got incremented by the current index value and our index got shifted. Next, what is the other option? The other option is that we don't include that element. So if we don't do that, our index will still shift, but our sum will remain as it is. And once we have the result of both these, I can simply return answer 1 plus answer 2. That is the total possible options. So see, what actually you have done here. You have believed on recursion that if you pass it something like this, it will give you the correct result. You have to believe it. You can't just go and just look for it. You have to believe that this function helper is returning you the correct answer. And once you start believing, because I have believed this, so what I did, I have simply returned answer 1 plus answer 2. Once you also start believing and how these things will come, that you are believing it, once the mind mapping, that is the recursion tree, gets clear to you. Recursion tree is actually the mind mapping of recursion, right? So once that thing becomes clear in your mind, so these things will come automatically. So that's the reason I have been speaking that try to draw a recursive tree for at least 4 to 5 problems. So once that is clear, the things will become like pretty much easy for you. So I hope this is clear. So this is what actually recursion is. It's not too basic as well. This question is not too basic as well. I try to explain you all how actually recursion is working by taking a very standard question. I would not say it is a very beginner question. The beginner question was something like this. The Fibonacci number that we discussed, that is something we call as beginner level problems. The beginner means the one who have learned recursion just right now. But this problem targets sum. This is something that I am not expecting you all to solve, but it is good and it will be super important if you understand it right now that how actually this is working. If you have not got it till now and if you are watching the recording, I would highly recommend you all to just give a pause over here and try to draw a recursive tree on your pen and paper. And once the recursive tree of this function becomes clear, then only move forward. Otherwise, there is no point of moving forward. The recursion will never get clear to you. So it's super important that you draw the recursive tree of this by yourself, understand it by yourself, code it down by yourself, and then move from it. Once you do that, just mark my words, the recursion will never disturb you. There are many high-level problems of recursion, but it starts all here. By writing the base cases, by making a recursive call, by doing small calculations, by returning the result. This is where the recursion starts. And once you understand that, the things will get super clear to you. I have one more question to discuss. I don't know how much I will be able to take it looking at the time. But yeah, we will not code it down, but we will definitely discuss what actually this question is saying. Just give me a minute. Yeah, I hope the question is visible to all of you. The name of the question is generate binary strings without adjacent zeros. So let's go through the problem. So you are given a positive integer n. A binary string x is valid if all substrings of x of length 2 contain at least 1. So you need to return all valid strings with length n in any order. So what actually question is? The question is that you have been given n. Now you need to develop a string of length n. Binary string actually. So binary string will contain either character 0 or character 1, isn't it? So you need to construct a binary string of length n. Now the constraint is that this particular string is valid only if every substring of this string that is of length 2 contain at least one character 1. So if let's suppose my string is something like this, so this is a valid string. Why? Because if I take any substring of length 2, it always contains at least one. So what are the maximum number of ones any substring of length 2 can contain? 2, right? So either it contain 2 ones or it contain 1. This is something that is not allowed. This is not a valid string because if you look up to this substring, it contains 2 zeros, and if we take this substring of length 2, so it does not contain at least one character 1, and so this entire string is not a valid string, isn't it? So this is something that you need to code. So this is the question, how we can do this. I want you all to write a simple recursion code for it. How we can do this? Just try to think. If I tell you that I made a function f in which I want you all to construct a string of length n. This is the requirement. Okay. Now, if I tell you that I already have a string of length n minus 1 constructed, would you not be able to solve this question? Let me repeat. If I tell you I want a string of length 6, a binary valid string of length 6, that is just handling all those constraints. If I say you that I already have a string of length 5, let's suppose that is also valid. That is also a valid string. So 0, 1, 1, 0, 1. I already have a string of length 5. If I tell you something like this. So now, would you not be able to give me a string of length 6 by using this particular string? The answer is yes. What are the strings you will return me? First of all, you will append 0 to it and you will say that, okay, this is also a valid string. And what is the other thing you can do? You can append 1 as well, and you can say that this is also a valid string because the string of length 5 was a valid string. This is something that is already given. Now you want to have a string of length 6. So you can either append 0 or you can either append 1, and you can return these strings as valid string, isn't it? So can't we make a recursive call to n minus 1, get the string from there and just append 0 or 1? But are you all able to identify, just observe one thing over here. What if the 5 length string was something like this? It is a valid string, right? It is a valid string. What if the thing was something like this? In this case, you can't append 0. This is the thing. In this case, you can't append 0, isn't it? The only option that you have is 1. Because if you append 0, so you will have a substring of length 2 that does not contain any 1. So you need to think on this, that if we can maintain something, that what was the last character we filled, the things will become easy. The only information we want is the last character that we filled was 1 or 0. If we have that information with us, the things will become easy, right? So we can maintain that we can maintain some flag, we can maintain that information and get our required answer. I already have this coded down. I will show that code to you all, but before that, just let me know if anyone is having any confusion in this till here, like understanding the approach, what actually we will do and how actually recursion is helping us. So let me go through the code. So see, so this was the function given to us. We wanted to return the strings of all the valid strings in this vector. So vector of strings. So we initialized, we have some vector string answer. We made one helper function. This is actually the recursion function that is going to help us to solve this. To this we are passing n, that is the length of the string we want to construct. Initially, this is actually the value of flag. If the value of flag is 1, if the value of flag is 1, this means that we have a constraint. The constraint is that we can't fill 0 over here. Why? Because the last character that we filled was 0. If the last character we filled was 0, we can't fill 0 again, no? So in this case, the value of flag will be 1. The value of flag will be 1. Otherwise, it will remain 0. If the last character we filled was 1, or if we haven't filled any character till now, the flag will remain 0 because we have both the two options available. We can either fill it with 0, or we can either append 0, or we can either append 1. Both options are open to us, right? So this is what actually flag will help us. So the value of flag is initially 0 because initially we don't have any constraints. Initially our string is also empty and our answer is something like this, the vector answer. We are passing this as well. Now just we will look to the base case at the end. If the value, just look up to the recursion call. If the value of f is equals to 1, that is the value of f is true, what does this mean? This means that the last character we filled was 0. We can't fill 0 again. So in our string temp, we simply pushed back 1 and called this recursion function with the value of flag as 0 and the number of numbers get decreased by 1. Else, we have two options. In our string temp, we can either fill 1 or we can either fill 0. So once we made a recursion call by filling 1, so we filled 1, made a recursion call, got all the possible answers via that, popped back 1, filled 0, and then made again a recursion call. This is actually what we call as backtracking. I know that many of you would find it overwhelming, but the only reason for taking this question for today's session is I want you all to draw the recursion tree of this. Because if you are able to draw a recursion tree of this particular question, then you will never face any difficulty in drawing the recursion tree. I will draw it for you all in this session so that you don't just need to roam here and there for looking for it if you are not able to do this. But if you want to try it by your own, just give it a pause and try it by your own, because it is something that will help you most. So and what is the base case we have? The base case we have is when we have the value of n as 0, that is we don't have any more numbers to put in the string, isn't it? In that case, we know that the string temp that we have is a valid string because we have kept in mind of all the constraints, isn't it? So in our vector string answer, we simply pushed back that string temp and simply returned from here. At the end, we know that this helper function will store all the value strings in this vector string answer. So we are returning answer from here. Let me draw a recursion tree for this so that the things will become clear. Let's suppose you had the value of n as 3. So we have the helper function with us. Let me write it as h. So initially we have 3 numbers to fill. The value of flag is 0 and the initial string is empty. Now since we have 3 numbers to fill, so we are not getting into base cases. So, and since the value of flag is also 0, so we have two options. We can either fill 1 or we can either fill 0. So let's first take by filling 1. So what we did, we made a recursive call by decreasing the number of numbers since we already have filled one number. And the number by which we have filled is 1. Since we have filled it by 1, so again for the next number, we don't have any constraint. So the value of flag will remain 0. But the other option is that we can fill it by 0. So the number of numbers will that is remain to be filled is 2, but the value of flag will become 1 because the number by which we have filled is, or the character by which we have filled is 0. Now again from here there will be a recursion call to h of 1, 0, 1, 1 if we fill it by 1. And again from here, if we fill it by 0, there will be a recursion call something like this. And from here, Again, if we fill it by, we have two options. Since we have one number to fill, we have two options, right? We can either fill it by 0 or 1. So if we fill it by 1, the value of flag will remain 0. And if we fill it by 0, the value of flag will become 1. I am not extending it further. This is something that you should try by your own. But till where I have extended, see, we have reached to the base case. That is, we don't have any more numbers to fill, isn't it? The value of this parameter n has become 0. Once that happens, we know that the string that we have actually is a valid string of length n, of this length n. So in our vector, we will simply push back these strings. We will simply push back these strings and we will get our answer. So this is how recursion would help you. This is how recursion is helping you actually. So wait a minute. This was a code that we actually wrote. So this was all from today's session. I hope all of you loved it. Wait a minute. Let me stop sharing. Yeah. So yeah, that's all from today's session. I hope all of you found it interesting. If you want to extend, if you are interested in taking this course, so kindly go to website TLEeliminators.com and just fill up the forms fast because the slots are filling up too fast. And yeah, this was a demo session for level 2. We already have demo sessions for level 1 and level 3 as well, which is the recording is already available. You all, if you all have any confusion, you all can even look up there as well. So yeah, that's all from my side. Thank you. Bye bye. Good night.